So today we are going to study the another method to get the optimal receiver, which is a matched filter receiver. So firstly, we would like to talk about the what is the filter, and I think in the signal processing course you already know what is the filter, and it you have some input signal, and you use some filter get your output signal, and well, it mainly performs some precision for your input signal, and to generate the output signal with your desired probabilities. And what are uh, uh, so there are two main filter types. First is frequency selective. Uh, it performs the separation of the signal based on the frequency. You want the high frequency, you want low frequency, you want the band, or you want the frequency band. So you can do such a operation, then you can get your desired frequency range. And the second is the matched filters, which is perform a search of the specific signal from the processed signal. And here I select a picture which shows our first what is the frequency selective, and you will see for here we have the low pass, and you need some cutoff frequency. So like here, you will get your cutoff frequency, and so here maybe we have the most used to use the cutoff frequency 3 dB or minus 3 dB, and we get the cutoff frequency. Now we use this part, and this is for the low pass, and we also have the high pass. We cut out the cutoff frequency. Now we will choose this part, and the band pass, which is limited to some specific band, like here. Here, and the band stop, which we will skip some band. So we only need this part, and some band we need some band, like here we need low pass band, or some the band pass. We need both. Now we just the same. We just cut off the frequency, and we get we wanted the frequency range here. Similarly for here, and pass. Or here it consists of the three: low pass, high pass, and band pass. And so this band, which we will use very frequently and common used in the signal processing. And filter for the zero sum signal processing component, and you will see here function tell us we need some input signal, and we need the filter, and now we can get the output signal. Here you will see the filter properties with the HT, which means usually we will use this um, impulse response. And here we need to do some operation, not is very easy integration multiplication. We here we use some convolution operation. So the S input signal will convolution with the filter. Then we get the output signal. And it can write as this integration expression. So let's do it. And it can write as the input tau and multiplied with t minus tau and d tau. So we did the integration to the to use the convolution operation method, and we can rewrite as it has some commutative role. We can change their position here, which we are seeing with the h tau multiplied with the as input t minus tau d tau. They will be saying. So for the H, we already know that we will usually we will use the impulse response, and so for the frequency response, which means it will be the H omega and their relationship. We can do some Fourier transform, which means this is for the frequency domain, and for t is a time domain. So we can do Fourier transform to get which what we would like. We want here. So for the filter impulse response, and we can consider the filter as a black box, and we don't know what its properties, and you will see the signal like a delta t. Output signal will be the ht, and usually the delta t is the third we know, and you can search some such signal like impulse signal, and after the filtering, and we can get such of the signal, and you will see its response. It can be the infinity. So we have the two impulse response, which first is the infinity. Impulse response, or second is the infinity. impulse response. And for the finity response, we will limit it as some frequency range Q. So we have the finite response. And for frequency response, it's usually the for the here you will see the frequency response, and as I mentioned, for the frequency we will get from the ht from the time to do the frequency Fourier transform to get the frequency response. You will see such here we have the cutoff frequency range. So this part will be the amplitude response, and we also can, for the amplitude response, we also can do some phase response. And this is phase, this is amplitude. So we can, according to its the impulse response, we can get more information via the Fourier transform. And for this picture, we already talked about in the channel, the channel, and for the channel also can be considered as the filter. And you will see here the fading channel frequency response, which this is the idea, the frequency response. You will see here we will limit it as some cutoff frequency and the frequency range will greater than the data rate. And for the real world frequency response, you can see here we have some distortion because of the worse transmission environment, and you can it's hard to get this distortion of the channel frequency response. And we need to know the impulse response. So here we can do some small conclusion about the relationship of the with impulse response. We have the here we have some time domain signal. Then we can do some Laplace transform to get the here frequency signal, and this is for Laplace transform. And as we'll do some we can use some polyform to get this one, and this is also can use some Fourier transform. Basically they are the same, and we have some transport function, and we will mention it in the next slide. And we also can do such replace, and we got our frequency response. So this is according to the frequency response, we can get our amplitude response and phase response. So this is basically their relationship. And what we already mentioned about the analog filters, you will see here we do some we got the analog frequency, we do Fourier transform from the time domain to the frequency domain. However, we still have some. This is for the analog filter. We still have some digital filters. So for the analog filters, we did some like Laplace transform or Fourier transform. Basically, they are same. However, for the digital filters, we did the Z transform. And this is the filter transform function. So we do here, we got no we will get according to this function to get the transmission function. And yes, will be so this is the transmission function, and we can get for example, we have some input signal and also do some Laplace transform. Then we multiplied with the transmission function to get our y. And we can use the output signal divided by the input signal. Then we can do some Laplace transform according some y_t, which has the Laplace transform with the xt. So this is the relationship from the time time domain and the frequency domain. So then we can go to the this formula, and we need to know some of the numerator polynomial bi, and the numerator polynomial coefficients here. We need to know both of them, their information. So, and similar for the digital filters, their relationship we can rewrite as z. So the transmission function will be the yz in output signal divided by the input signal, and we can do some z transform for the time domain output signal divided by the z, the input signal in the time domain. This is a basic relationship between the input signal, output signal, and the transmission function. So we need to design the filter, and we need to know the filter order and the numerator polynomial coefficient bi and the numerator polynomial coefficient ai, which means we need to know how many b here and a the number of b a, and we also need to know the how to say, here we have the order. How many order do we have? And the next slide, we are going to talk about the matched filter. So in order to design such of the filter, we need such a specific partner in a signal. And here, this is for the noise signal, which means usually we got from the real world as we already have some practical work, and you know signal hidden in the noise signal, right? And we need to find out the hidden signal, and I will mark it here, and this is the hidden signal in the noise, in the received signal, uh, which has the adaptive noise evasion function. I think you already know that. So we need to find this hidden signal, and however, we need to know some specific partner. Here we have some partner, and partner, which means it's a reference signal, and it will help us to find out where is the hidden signal. And let's move to the video part. And this is the this is the beginning part. This is hidden signal beginning part. Let's see. And you will see after the movie and our mm, the filter output will has a decrease, and the arranger here, and it will increase again. So when it increase and very fastly and increase, so we reach to the maximum point here. After that, what will go on? How it will keep the state here, or will just decrease? Let's see. So it just decrease. So it just decrease. So in the matched output, we can get our get the very important information. We have the maximum possible value, which can tell us where is the hidden signal height. Where is the hidden signal? And you will see in the here same x-axis point, like here 100, and here. So it's same with here, same as here. And this point, we can find our desired signal. And in order to realize this function, such as function, we must need to know a specific partner. And here is question: how to put in the filter structure the pattern used to research? So their relationship is we have the input signal, which has the noise signal, and we send to a filter, and we add some pattern, which means a reference signal inside. Then we can get the output YT, and it will tell us where is the pattern hidden. And so the pattern is the filter impulse response, which is equal to the filter impulse response, and it must contain this information. And we can see an example here. And you notation here, X is the input signal, and the TA is the target signal, which means a pattern. It is a pattern, and YA is the output signal. And for the input signal, we need to know here is the hidden pattern, and the T is the pattern which we use. And for the output signal, we need to find out maximum point, which will tell us where is the hidden pattern, and it will tell us where is the real here where is the signal here. So we do some calculation here, and here has some filter, and it has for filtering the equation, and the filter calculates the convolution operation, which I already mentioned. And we have the input signal, and we have the pattern, and the reference signal. We do some operation, convolution operation, and equal to some multiplication, and to do some integration. And this is for the analog case, and for the digital case, we do some multiplication, which L is the order of the filter, especially for the finite impulse response. And for the infinite impulse response, it's mainly used in the analog case. So put next, and you will see here there is some notation here. The convolution formula flips the impulse response, which means here the convolution operation is flip the impulse response, and we need to reverse it. You will see here is a t minus tau, and here we use the ts minus t, and ts is the duration of the symbol, and a is the arbitrary constant. Usually it can be considered as the one. So this function represents the impulse response in the time domain. And here we have an example. It's a 8-bit asked to calculate the target signal, and we need to design it match filter impulse response very easy. We just mirror that signal, then we can get it impulse response. And for the next slides we will talk about what's the relationship between the correlation and the convolution. We already studied the optimal correlation receiver, and well, the convolutional operation also very similar to the correlation. So here we have the received signal UT, and it can be to signal, which is S1T, usually be considered as the 1, S2T, considered as the received signal as the 0. This is UT received signal. Then we multiplied with the SIT, which is carrier signal, and we have some specific time period with the TS, and we did the integration. This is for the correlation received signal, and for the matched filter, we did some convolution operation. As I already here, we have the received signal UT, and we did some convolution with the impulse response, which means the HIT. So here is the received signal. Then we do the convolution with the impulse response, and it can rewrite as here similar to the correlator operation. We can multiply it with HT minus tau, and we have some specific time range. Then we do the integration. So, and here we can see HT can equal to the TS minus T. It's we did a flipper here. All we need to do here, we need to do such a flip here, and now we can consider use the T. We can consider and to use the tau represent the H tau will be the SI TS minus tau, right? And usually in our case, tau is equal to T divided by the 20, right? And we set as like this, and we can see here the T minus T. No, so sorry, we can compare here. So continue is we can represent to put this in back to here. So T minus tau will be the TS minus T minus tau, right? And which is similar to our case. We use the substituting impulse response, and here we have the range here, like here, and it will be similar to the correlator, and it will increase. we have the stopped here, stopped the range here, and we have the threshold here. So this is case we can do some we can use some that's it. We can use some we can consider use the t equal to ts to represent to get represent this point, because it we can get in this point we can get a maximum energy here. So if the t equal to ts, then we got this equation, and after sort we can get this one. The here receive after the match the received signal will equal to the t the received signal multiplied with the impulse response, and we do the integration here, and it seems to the which the result is same to the IT correlation integration here. You will see here that just the difference is that here use the t and here use the tau, and I already mentioned the relationship between the t and the tau. And for the result, we can know here if the ut equal to the sit, it will be the energy. However, if they are not same, so we just do the no. If they are not equal, they are just 0. And for the convolution, and you will see here we have the specific case with correlation, which one the signal is mirrored, and this mirror we need to perform this mirror for the optimal receiver is compensated by mirroring the filter impulse response. So here we have the mirror twice for the target signal. And for the HT, the filter impulse response, we need to mirror it. Here, we mirror it. And for the optimal receiver with the matched filter, and the basic idea similarly here, we have the binary data. We let it pass to the adaptive white Gaussian noise channel. Then we get the received signal, and we do the match filter, and it will after the match filter, you will see it will increase at some maximum point here, at some maximum point. Then we can give it as some threshold. You will see here, like 0, such as the threshold is 0. If the signal greater than 0, it's 1, and 1, and if it's less than 0, and it will be considered as 0. So it will 1, 1, 0, 1, 1, and so here the basic idea is quite simple, and the only things we need to do is design the correct matched filters. And for the matched filter receiver, we can see here the correlator receiver and the matched filter receiver are very similar. So first step, we need to design a matched filter for each non-single type, which means you will know what single is for your transmitted. Then you can design your matched filter. However, if you don't know, so it's very hard to design. And we send the received signal, which combined with the noise to each matched filter, you will send like S1, S2, or go on, like different carrier signal. Then next more, you can do some sampled filtered signal, and you will find the increased maximum point. Then you will find the hidden pattern. So this is the basic idea. And you will see here, this picture will quite similar to the correlator receiver. However, we did not need to do more design like multiplication or integration, such like things. And we just consider this box is the filter. And we send the received signal inside to the filter, and we have some impulse like finity impulse response. Then we do the operation and integration. Next, we send to here, and we can get its energy, right? As mentioned, we will center the different singular energy, which are around the 0. So if we have the multiple signal, then we need for each of them we need a matched filter, and we can get the multiple energy signal energy. However, if they are same, we just skip this step, and we will send to the decision and to compare it with the threshold or their selves. Especially in the frequency range, we have 2 frequency. Then we just compare them, which one is good. So then we make the decision. So it's similar to the correlator receiver, but it will more clear. And here has some shortcomings of the matched filtering. Firstly, we need to design the filters with the specific impulse response. As I mentioned, you must know what your received signal, the component, such as it's carried signal, or which is so we must know the received signal, and then we can design the impulse response. However, it's not very always possible because especially in the analog form, and it's hard to design such a infinite impulse response. And we already know that the channel also can be considered as a filter. And if the channel has some distortion, and we need to know channel impulse response as well. However, it's also hard to know because you you cannot know uh, well the channel will change very fast if in the mobile communication, right? Because you will moving, you will get uh, the channel's environment is not stable, right? And it will change very fast. So each time you will get, you hope you want to get know the uh, corresponds the channel impulse response. So it's very difficult. And uh, and for the operators in some continuous mode, and it's also very hard, difficult to design some analog component. So in the correlator receiver, Dr. Ennis, he already introduced some analog components in here. He just skipped this step, and very hard to get to design and to get the analog component. And this thing for you can, if you're interested in the more details, you can just study it for uh, the matched field receiver. So today's lecture is over, and next lecture we are going to move to the practical exercise, the fifth practical exercise. And after that, we have one more course project course project questions. I remember that is six problem. So we can start at 9:35. 9:35. So see you soon.